In the previous lecture, we have started to discuss the waves in warm plasma, particularly in case of non-magnetic and non-collision plasma. And in this regard, you have seen some of the important assumptions. On the basis of those assumptions, actually we have obtained a wave equation, and that result was actually the last result of the previous lecture. So for your convenience, I have actually repeated here all those assumptions so that the today's lecture will be easier to understand. So let us see what we have actually assumed in the discussion of waves in non-magnetic non-collision warm plasma. So you have seen that actually our first assumption was that our plasma is sufficiently hot and thin, and in such a medium, when the plasma is thin and hot, it is obvious that collision in that medium will be negligible. And another important assumption of ourselves were that gravitational pull is also negligible. Gravitational pull is negligible. And no external magnetic field is present, as the heading says. This is non-magnetic case. So here this B represents actually the magnetic field which has been applied externally, but it is zero, you can see. Now in such type of plasma fluid, when a wave travels, then actually the propagation of the wave is just like the propagation of sound wave through air. And you have seen in the lower classes the propagation of sound wave in air, where you see that actually such propagation of sound wave takes place adiabatically. So in the first part of this lecture, we have actually used the equation of a state for a perfect gas in case of adiabatic process, as this thin and hot plasma behaves just like a perfect gas. So using the MHD equation, after that the equation of continuity for charge conservation, and equation of a state for perfect gas, actually after all those calculations we have arrived to a particular result, and that result we can see here. This was actually the final, or you can say the last result of our previous lecture. I have mentioned that result here for your convenience. You can see the last result which we have obtained in the first part of this lecture was omega square p, omega p square rho e minus gamma kbt over m del square rho e plus del 2 rho e by del t square equal to 0. Actually this is the wave equation, and in this equation you can see this del square is Laplacian, and this omega p is what? You know, this is the well-known plasma oscillation frequency, which is given by a square root of Ne square by m epsilon naught. You know it. You have already studied this in the heading plasma oscillation in the previous videos. And this rho e is volume charge density, and it means this is volume in unit, this is charge in unit volume. And as you know, this N is number density, that is number of plasma particle in unit volume, and E is charge of one of the plasma particles. So Ne represents the total charge distributed or content in unit volume, and that is called actually rho e, that is volume charge density. And in fact, in this equation A, which I have called it that it is a wave equation, and in this equation you can easily recognize that this function rho e actually acts like a wave function. Now we will see the solution of this equation A. In fact, you know the wave equation has in fact several types of solution, but for convenience here we will write the plane wave solution of this equation. So you know how we can write the plane wave solution of this equation A. So the plane wave solution of equation A. What will be its plane wave solution? You can see this can be written as rho E equal to rho naught E to the power I k dot r minus omega t. You know it. And say this is equation 1. You know here this rho naught E actually acts like the amplitude of the wave function, amplitude of the wave you can say. And what is this k? You know this k is wave vector or propagation constant. This is wave vector. And this omega is actually the cyclic frequency of this wave. Cyclic frequency of the wave. Now actually, as I have told you in the first part of the lecture, that in this discussion our main purpose is to find the dispersion relation for warm plasma. And to get the dispersion relation for warm plasma from this resulting equation defined in A, actually first of all we will change the form of this equation A by using the two alternative operators. Actually those operators you have already studied during the study of cold plasma while we have discussed the clean Gordon equation, and also you have seen it in the study of electrodynamics. In fact, this form of equation which has been defined in this equation 1, mathematically from this equation 1 we can obtain two operators from this equation 1. And what are those equations we have already discussed earlier. So I will write those two operators here directly. So you can see from equation 1, it is found that I am not going to evaluate it because we have already evaluated in the previous lectures. It is found that, in fact, when you will use that equation, you will find this del operator, which is just, you know, this is gradient operator. So del means gradient. So del equivalent to grad. And this is equal to actually ik, where you know this I is for iota imaginary, which is a square root of -1. And this del t operator, from that equation you will find that this del t will be equal to -I omega. And so from here we can easily find the second order derivatives. So you can see what will be this del square, that is Laplacian. You know del square is simply del dot del. And you can see since this operator del is ik, so this will be ik dot ik. And you know this I dot I will be I square, which is -1, and k dot k is in fact k square. So this is simply minus k square. So this operator, that is Laplacian del square, may be written as minus k square. And again, the second order partial derivative with respect to t, that is del 2 by del t square. This can be simply written as minus I omega times minus I omega, because you can see del t is minus I omega. And here this minus minus will become plus, but again I square, which will be minus 1. So this is also minus omega square. Now let us make the use of these two operators, that is del square equal to minus k square and del 2 del t square equal to minus omega square in our wave equation, which we have actually defined in this equation A. You can see. So see this equation and then replace the del square operator and del 2 by del t operator by their corresponding values. So using these in equation A, using these in A, we get what you will get. You can see actually the first term is omega p square rho e. So that term will remain at its. So this is omega p square times rho e. And second term is minus gamma kbt by m del square rho e. But you have seen that this del square operator is minus k square. So we can write the second term as plus gamma kbt over m times k square rho e. K square rho e. And last term is del 2 rho e by del t square, and you have seen that the operator del 2 del t square is equal to minus omega square. So you can write the last term as minus omega square rho e, and this equal to 0. This equal to 0. You can see. Now this equation A has been changed into that form, and let us simplify this result to some extent. You can see that we can take this rho e as a common factor because it is present in all terms of LHS. So we can write it as omega p square plus gamma kbt over m times k square and minus omega square rho e equal to 0. And as you know that this rho e is not equal to 0 because it is volume charge density of plasma medium, so definitely the term inside this bracket will be 0. So you can see that this omega p square plus gamma kbt over m times k square minus omega square equal to 0, because you know this rho e is not equal to 0. Now from this equation we can easily find what will be the value of this omega. So you can see this omega square will be equal to omega p square plus gamma kbt over m times k square. And so if you want to write the expression for omega, you will simply put the square root in RHS and so you can write this in this way. So if we remove here a square, then we will simply put a square root in RHS. So this is actually the value of omega as a function of the wave number or propagation constant or wave vector k, you can see. And as you know, the relation between this omega and k is actually called dispersion relation. So this equation 2 is nothing, this is simply the dispersion relation for warm plasma. So you can say this is dispersion relation for warm plasma, you can say. Now this relation which we have defined in this equation 2, which is called dispersion relation for warm plasma, actually this relation can be expressed in a very important in terms of a very important parameter which we have already studied in the previous lecture in the beginning, and that is actually called device screening radius or device screening length or device screening distance. So now let us see how we can express this equation 2 in terms of device screening radius. So let us try to introduce the device screening radius in this equation. Now for this you can see this result omega equal to this much may be written in a particular manner. You can take this omega p square as a common factor in RHS. So now let us see, this omega is equal to, when you will take omega p square as a common factor, and since this is inside the square root, so in outside it will be simply omega p. So this will be omega p, and at the place of first term you can see there will be 1, and as in second term omega p square is not present, so we will simply divide this second term by omega p square, and so you can write this is 1 plus gamma kbt over m into k square and divided by omega p square, because the second term does not contain omega p square. Now as you have seen earlier just now, you can see here this plasma oscillation frequency, I have defined it here, and we have studied it in plasma oscillation discussion. So now we will substitute the value of this omega p which we have defined earlier. So as you know, what will be this omega p square? Actually omega p square will be Ne square over m epsilon naught. So let us put this value of omega p square in this equation here, and therefore you can write this omega is equal to omega p times 1 plus gamma kbt over m times k square times 1 over omega p square. So it will be written as m epsilon naught over Ne square. Is it not? You can see this will be the result. And now let us see some of the simplification. You may see here this m will cancel out, and our result will be omega p times 1 plus epsilon naught kb times t divided by ne square. I have written this factor inside a bracket due to some reason which we will just see. And apart from this factor, in our expression there is gamma and k square. So let us write gamma times k square. Now see this factor and think, what is this? You have already studied in this factor previously. So I am just asking you to recognize this factor. If you see this expression seriously, you can easily recognize when we were actually discussing the device potential, then you have seen that this expression inside the bracket, that is epsilon naught kbt over ne square, is nothing. This is simply a square of the device screening distance. So in turn, now we can introduce the device screening distance here. So you can say as lambda d is equal to epsilon naught kbt over ne square to the power half, and this is what? This is known as device screening radius or length. Device screening radius. So in terms of this device screening radius, you can see this equation which we have obtained can be written in this way. So you can write omega is equal to omega p times 1 plus gamma lambda d square k square and whole to the power half. Actually this is also dispersion relation, but we have expressed the dispersion relation for the warm plasma in terms of the parameter lambda d, which is a well-known parameter known as device screening radius. Now if we will talk particularly about electron, then you have definitely studied that this adiabatic exponent gamma for electron is equal to 3. So you can say for electron this gamma is equal to 3, and therefore omega can be written as omega p times 1 plus 3 lambda d square k square. But this is a special relation, because this relation will be valid for electrons only, because for electrons gamma is equal to 3 and we have used the value of gamma 3. So this is particular result for electron. And so in accordance with these equations, you can easily see that the frequency of the wave actually depends on its wave number k, and so with in change in k, this frequency will change, that is d omega by dk will be not 0, and the variation of omega with k, that is d omega by dk, is actually the measure of dispersion. So this result is known as dispersion relation. So in fact in this two lectures, our aim was actually to find this dispersion relation for the wave in a non-magnetic, non-collision warm plasma. Now in the next lecture we will see actually waves in non-magnetic collision plasma. In this we have not considered collision, we have neglected the collision, but now we will again discuss waves in non-magnetic plasma, but that plasma will be not non-collision, that will be collision plasma.